Hi everyone. In this video, we'll discuss what is pre-stress modal analysis, how does the pre-stress affect a system's vibrational characteristics, and how to perform pre-stress modal analysis in Ansys Mechanical. Let's go. A modal analysis determines the vibration characteristics such as natural frequencies and mode shapes of a structure. It often serves as a starting point for several linear dynamic analyses, such as a transient dynamic analysis, a harmonic analysis, or a spectrum analysis. The mode frequencies and shapes depend on the distribution of mass and stiffness in the structure. When a structure is in a stress state, its stiffness changes due to stress stiffening. Therefore, the presence of stress in a structure can alter its vibrational characteristics. Typically, the tensile stresses increase the structure's frequency and the compressive stresses decrease its frequencies. A few examples where we can see the pre-stress affecting the mode frequencies are in the tuning of a guitar string, where the tension in the string is adjusted to change its frequency, in slacklining, where the rope is stretched and the tension in it prevents it from wobbling while walking on it, and a rotor that is spinning very fast as it deforms under the centrifugal forces and is therefore in a stress state. Performing a modal analysis on such pre-stressed structures is called pre-stressed modal analysis. Let us now investigate the governing equations associated with the modal and pre-stressed modal analysis and see what basically changes between the two. In a modal analysis, we obtain the natural frequencies of the structure by solving this equation. Here, K is the stiffness matrix and M is the mass matrix of the structure. When there is pre-stress in structure, the change in its stiffness is captured by adding a stress stiffening matrix S to K. Therefore, in a pre-stressed modal analysis, the governing equation takes this form. In terms of workflow, to perform a pre-stressed modal analysis, we first perform a base stress analysis. This analysis can either be static or a transient analysis. Also, it can be either linear or nonlinear. During this analysis, we compute the stress stiffening matrix S, and in case of nonlinear stress analysis, we also capture any changes in the stiffness and mass matrix. The mass of the system may not change, but if the center of gravity of the system changes due to rigid body motion or very large deformation, those changes are captured here. In Ansys Mechanical, we restart from the base stress analysis and use the linear perturbation technique to perform pre-stressed modal analysis. A few things to remember about pre-stressed modal analysis are: if the base stress analysis is linear, then the modal frequencies are calculated with respect to the undeformed mesh. If it's nonlinear, then the mode frequencies are calculated with respect to deformed mesh. Also, any changes in stiffness and mass matrices due to material or contact nonlinearities are captured at that moment and updated during the modal analysis. It's worth noting that the presence of stress may not always affect the mode frequencies. For instance, if the stresses are localized, then they may not impact the system's frequencies at lower modes. Also, the stresses reported by a modal analysis are relative, and their absolute values do not hold any physical meaning. Now let's go ahead and see how pre-stressed modal analysis is done in Ansys Mechanical. In this example, we'll use a bar with square cross section constrained on both the ends and kept at a room or reference temperature of 22 degrees centigrade. We will subject this bar to thermal load, which will generate thermal stresses in the bar. Let's take a minute to understand this setup. The total strain developed in the part is equal to the sum of elastic and thermal strains. In the axial direction, since the bar is fully constrained, the total strain is 0 in all cases. Therefore, the elastic strain developed in the bar is equal in magnitude but opposite in sign compared to the thermal strain. So, when the thermal load is more than the reference temperature, the thermal strain is positive and therefore the elastic strain is negative, which implies compressive stresses are developed in the bar. Similarly, when the thermal load is less than the reference temperature, the thermal strain is negative and therefore the elastic strain is positive, which implies the tensile stresses are developed in the part. The goal of this study is to see how the mode frequencies of the bar change with the thermal load at 5 different values. We'll perform a parametric analysis to run a series of simulations and study this trend. Each simulation is called as a design point. Drag and drop a static structural analysis onto the project window. Drag and drop a modal analysis system onto the solution of static structural analysis. Notice the connections that are created. Materials, geometry, and other model details are shared downstream. This connection implies that the solution from static analysis is used as a setup for modal analysis. Such a system is also predefined under custom systems as a template that can be used too. Now, attach geometry to system A and open mechanical. We'll use structural steel as the material assignment for the bar. Select the two end faces and define a displacement boundary condition and set x equals to 0. Next, select two edges from both ends and define a displacement condition of y equals to 0. And select the other two edges and constrain that displacement in z direction. This way, the bar is constrained in all three directions and yet free to uniformly deform between the constraints. This creates a uniform state of stress in the bar. Next, select the bar body and insert a thermal condition to define the thermal load. Set the temperature at time 1 second to 0 degrees centigrade. This is less than the reference temperature, which is 22 degrees centigrade. So tensile stresses are developed in the bar. Now right click on solution and insert normal stress. In this demo, we'll extract stresses in axial direction, which is global x direction, and it is the default option. So leave it as is. Now solve the model. There are positive stresses developed, which implies that the bar is under tensile stress. Now moving on to the modal analysis. If you click on pre-stress, you can see the base stress results from which it extracts the pre-stress information. The boundary conditions are already defined in static analysis, so we need not define them again. Go ahead and solve the modal analysis. We get the mode frequencies for this system. Select the first mode and plot the mode shape. Evaluate results. Now let's parameterize three quantities: thermal load, average normal stress, and the frequency of mode 1. Go to Workbench and we see the parameter set created. Thermal load is identified as input parameter, and normal stress and mode frequency are identified as output parameters. Next, we define the other design points by changing the input parameter, which is thermal load. Notice that at a thermal load of 22 degrees centigrade, the bar is in a stress-free state. Now click on Update All Design Points to solve for output at other design points. Once the solution is done, insert a parameter chart. Set y-axis bottom to normal stress. Set y-axis left to thermal load. Set y-axis right to mode frequency. Now right-click on the plot and select Edit Properties and set Legend to Visible. We see that as thermal load increases beyond reference temperature, the stress state in the bar changes from tension to compression. As compressive stress increases, the mode frequency decreases. As tensile stress increases, the mode frequency increases. Therefore, we can say that the presence of non-zero stress in the part changes its modal characteristics. This completes the demo. Now let's summarize what we learned in this video. Stresses developed in a part change its overall stiffness due to stress stiffening, and this can change its mode frequencies. A pre-stress modal analysis is used to calculate the modal characteristics of a structure with inherent stress. A base static or transient analysis is performed to calculate stresses, followed by a modal analysis using linear perturbation technique. The base analysis can either be linear or nonlinear, but the modal analysis is linear in nature. I hope that you have found this video useful. If you like this video, then please like, share and comment. Also, do subscribe to this channel to receive updates and visit ansys.com/courses to discover more useful content.